Okay. Mute or sorry.
Yes, sir. Unmuted. We can hear you. Well.
Yeah, hello. Good afternoon, everyone. Good afternoon, sir. Good afternoon, guests online, and good afternoon all to all the participants who are assembled in this hall. So this is basically an important event for everyone on this planet, actually, right? In particular, to my students at JCE campus, we have conceived this program through our student club members, like Stella JCE is a very young club on the campus, mentored by Department of Electronics and Communication Engineering, and also we have hardware club members, volunteers. So once again, mentored by electronics department. So and my Gnanam team, Gnanam members, and also team IEEE members. So it's basically a group of all these students, very highly motivated students who are here making this program a success. I call this program as a celebration. Actually, it is just like celebrating any other festival across India in Indian way. So we are here to clap the people who are behind this program. So it's a pride moment for everyone on this planet, in particular to Indians. In specific, it is to my students on this campus. I welcome you all to this celebration event. Welcome you all. So before I just talk, I just open my opening remarks. I bow my head sincerely to Sutturu Guru Parampara, which made this institution, this campus, a fantastic place for learning. Okay, my pranams to the Sutturu Guru Parampara. Moving on, I take this opportunity to welcome all the guests of the university, sir, across the campus, across the university, sir, to all the officials across the university who have helped us to organize this program and to carry on this message of this beautiful event. We also welcome our head of the department, Dr. UB Mahadev Swami, sir, and also our mentor, Dr. Sudarshan Patil Kulkarni, sir. I call upon them to occupy the dais, sir. Please welcome it. This is basically a blended event that's happening online as well as offline. So even though we know that many of the videos have been uploaded live stream, we wanted to have a small interaction with my students. So we have our honorable guests online, Shri N. Srinivasa Hegde sir, former director Chandrayaan-1 mission. We all join to welcome Shri N. Srinivasa Hegde. Please join hands to welcome. We welcome you, sir. We also welcome Sri Ananta Krishna, Director. We all join to welcome Mr. Ananta Krishna. We welcome you, sir. We also have one more guest, Dr. S. Rangarajan, Director ISRO. We join hands to welcome Dr. S. Rangarajan, sir. We also welcome our important guest who is associated with our Gnanam program, Dr. Jayakumar Venkateshwaran, CEO, Wallace Marineries International Private Limited. Join your hands to welcome Mr. Jayakumar. We welcome you, sir. I also take special opportunity to welcome our head of the department, Dr. UB Mahadev Swami, who is behind this program. For all our program, he is always giving a positive response to organize any other important events. We join hands to welcome Dr. UB Mahadev Swami. Conceiving such a program to organize and to taking this flag of learning to the students is an important concept. Basically, we need to conceive this program, make it practical such that it reaches my students. So for this, we have discussed in lot in the department, and especially Dr. SP Sudarshan Patil Kulkarni, sir. So we welcome you, sir. Please join hands to welcome. Thank you. We also welcome the faculty of ENC department and also the faculties from various other departments who are present offline, online. Please join hands to welcome all the faculty members who are present online and offline. Thank you. Very importantly, we made an elaborate dissemination of information across the campus to all the students, especially my first year students, the second year students. The higher students are actually on the vacation actually. So I take this opportunity to welcome all my student members, my young minds here who are curious to know these things. So please join hands to welcome my young minds in this hall, online, offline. We welcome you all. Special thanks to the groups Team Stella JCE, Team Gnanam, Team EC Hardware Club, Team IEEE. A special welcome to these students because these are the people who are pioneering this program. Thank you. Wait, next. Next person. Introductory remarks by Sudarshan Patil. Call upon Sudarshan Patil. I call upon.
Now we call upon Dr. Sudarshan Patil Kulkarni for the introductory remarks of this event.
Good afternoon, all the faculties and higher officials who have joined online and all the students who have assembled here for this very exciting day of launch of Chandrayaan Mission 3. A special welcome to our guests, Shri Srinivas Hegde, Shri Anand Krishna, Dr. Rangarajan and Dr. Jaikumar Venkatesan. So this is a really very thrilling day for Indian science because this is the third mission to Chandrayaan. Okay, as an engineers, okay, we always go by the efforts. Okay, whether it is 100% success, 90% success, that analysis is later. What matters is we are putting the efforts to achieve something. Okay, so the scientists have put a lot of effort. Okay, to do this kind of a mission. It takes years, planning. Taking approvals, licensing, building teams, and each team works on a certain module, and that all those modules need to be integrated, and finally we are there for the launch. Okay, so while it looks very fascinating on the day of the launch, behind that there's a lot of sweat and blood of our scientists. That is what we need to applaud and we need to appreciate. And that is why we are here. Okay. And as many of you know, JSS is also involved in a JSS nanosatellite project, and the team is experiencing the similar effort, but in a nano scale. Okay, in terms of taking approvals, procurement, building teams, designing, all those experience we are going through in a very nano scale compared to Chandrayaan. Okay, but we relate to the ISRO scientists. We appreciate their efforts. Okay, I'll just give you a brief bio of our eminent guest, Shri Srinivas Hegde. He had his earlier education in Karkala. He did his BE Electronics and Communication in Surathkal and Masters at IISc Bangalore, and he has been with ISRO from 1978 to 2014. And post-retirement also, he's involved in many space activities with the Team Indus, etc. and he's a very knowledgeable and eminent person, and we're really thankful that he's with us to answer our questions and interact with us. Okay, we also have our technology partner, Vales Magnals International Private Limited, it's Jaikumar Venkatesan. He is also very experienced with several space projects, including some missions to the moon. So we wholeheartedly welcome him, and they are all here to enlighten us. Okay, I will not waste the time, and let's move on. Thank you.
Now we call upon our guest speaker, Shri N.S. Hegde, sir, joining us online.
Good afternoon. I was fortunate to get involved with the moon missions, I think from 2000 onwards. So that was the formative year of Chandrayaan-1. We made the study report, and Chandrayaan-1 was eventually launched in 2008. And although it lived only for 10 months, it gave us a tremendous experience in operating all the 12 payloads. And it was really useful to know the moon's atmosphere, and which paved the way for the future missions. And after retirement, I was fortunate to get involved with the Team Indus, which was a private venture which was trying to land a small craft onto the moon. That way, my experience continued till 2020. Now I am associated with a small private company for manufacturing small satellites. Okay, basically, okay. So rather than explaining how we go to the moon and all, I would like to tell the importance of going to the moon's poles. As you know, Earth has got.
Can just help you out how to post the PowerPoint presentation in Google Meet?
Share the screen. How to share the screen? Any idea?
Sir, you can you can move your cursor. There is a hand button next to the button is present now.
There is arrow mark up, present now, yeah.
That you can click and select the screen share. You can press the button, sir. Present now.
And your entire screen is there.
Yes, sir. You can view the entire screen and you can open your presentations.
Presentation.
You can select the window entire.
First, I have to open the presentation, no?
Yes, sir. Correct. You can present. You can share the screen, sir. It shows the entire screen, and click. You can move the cursor down and select the screen. There is like small preview will be appear.
Yeah. First, I have to open the.
Sir, otherwise, can I show it to you how to do it?
No, I have opened the presentation here.
No. You can present now. You need to click the button present now in the Google Meet.
Present now, entire screen.
Entire screen, and you can move the cursor down to select that preview. One preview box. You need to select and then share. If there will be share button will be enabled.
Share button. Share button.
Once you click that preview, and it will show you, sir. Share.
No, me too. No, I've opened the presentation.
Yes, sir. Correct, sir. It's sharing. We can see it. Thank you.
You can see the presentation.
Yes, sir. You can open your presentation, sir.
Yeah.
Yes, sir. Super. You can make it a full view. Thank you, sir.
Is it audio, visible?
Sir, you need to open the presentation actually. Yes, coming, sir. You need to we have to make the full size, full screen. Yes,
Okay.
sir. We can see you, sir.
Next. Okay. Our way of going to moon, because of the limitations we didn't have a huge rocket, but we had adequate rocket like PSLV, which could launch a 1000 kg satellite in a geotransfer orbit sort of thing. Then we had craft with enough propulsion which will carry it to the moon. That is the way we went to the moon in case of Chandrayaan-1. A variant of that with the GSLV Mark III is what is going to happen today on a much higher scale.
To be more precise, once we launch, we orbit around the Earth till we wait for an appropriate event for the moon to come in visibility, so that we'll be in the Earth. In the meantime, we'll raise the apogee to a certain height of almost to 30,000 kilometers, and then to 80,000 kilometers. Then at final shot, we'll leave the Earth and proceed towards moon. That we call it as TLI, translunar injection. So in that phase, it will take about 5.5 days to reach the moon. And then once it is in the vicinity of the moon's sphere, we capture the moon, leaving the Earth's gravity. So this is the process which we started in Chandrayaan-1. The same thing followed in Mars as well as for Chandrayaan-2 and 3.
So this is the basic geometry of the moon mission. As you can see, this is the diagram which shows Earth going around Sun and Moon going around Earth, and orbit is shown as a dark one strip. That is the inertially fixed orbit. The orbit is inertially fixed, and very interesting thing is, see, Sun apparently moves with respect to Earth plus minus 23 degrees. It's the apparent motion. But with respect to lunar equator, Sun moves only 1.3 degrees. As a result, what happens is the poles of the moon are never illuminated fully. So what happens is, and moon is lot curvier than Earth, and the sun never rises above too much above the lunar equator. That's why on Earth we have something concept called Arctic Circle and Lapland region. That is 70 degrees latitude onwards. We have a region called both the poles called Land of Midnight Sun. That is around June 21st. The North Pole will be continuously illuminated, and all the Scandinavian and northern Canada will be continuously illuminated. This happens on the moon in a different scale. On the moon, 88 degree is an equivalent of Arctic Circle, or that 70 degree equivalent of on Earth. As a result, after when the moon and Earth got formed after the collision, they both stabilized their spin axis in inertial space. As a result, inertially, the axis of the moon is so stable, and the sun will never get to see the poles, but it will graze at an angle of say 1.33 degree at the pole, and at 88 degrees the sun rises maximum around noon to 3.3 degrees. So because of this land of midnight sun type of geometry, as you know, moon has got only 12 days. Earth has got 365 days. Moon has got only 12 days. One lunar day is equal to 28 Earth days. That means 14 days of sunshine and 14 days of night at the mid latitudes and at the equator. But at 88 degree, a very interesting geometry starts. You get one lunar day of 25 days of sunlight and 3 days of night. when this happens at the North Pole, in the night, South Pole, three days of night and 3 days of day and 25 days of night occurs. So this is the geometry. Suppose we get into this region, which is 88 degrees and above, then we have we can explore with all rover and all more meaningfully, and you have sunlight for more than 20 days. But of course, it is just a grazing sun. But going there is so difficult because the land is quite having lot of craters and all. The chosen latitude for the Chandrayaan-3 lander is 70 degree. The 70 degree is far away from 88 degree. So here the geometry is 14 days of daytime and 14 days of night. Okay, why poles are of the moon are very interesting is because the poles have got craters which have never seen sun since billions of years. Because they have not seen sun since billions of years, what is assumed is, and okay, as we know, sun doesn't have a magnetosphere also, so there is nothing which protects from solar wind. So solar wind and solar mass ejections will deposit a lot of volatiles on the lunar surface. These volatiles, on receiving further the solar energy, they keep on jumping with a Brownian motion, and by probabilistic calculations, it is estimated that the cold traps which have never seen sun both at the North Pole and both at South Pole are supposed to contain very important volatiles like helium-3 and deuterium and all important materials which are important for fissile, easy fission. So this is the nearest place where we can get material volatiles required for fusion. Because of the it is easy to generate start fusion with these kind of volatiles. This is the place where China or India or USA are racing to get. But the problem is the cold traps. The temperature is very close to 4 Kelvin. 4 Kelvin, all the material characteristics change. How to mine this is a very difficult proposition. Okay, this is about the race towards the cold traps. And right at the South Pole, there is a crater called Shackleton. The Shackleton crater is right on to the South Pole, and the crater shoulders are jutting out. So the crater shoulders are above the pole. As a result, some interesting geometry takes place called um, eternal light region. That is, the peaks of the crater shoulders are having 100% illumination throughout the year because the sun is just grazing on the pole, and the sun moves. If you draw a parallel to equator at the pole, sun moves only 0 to 1.33 degrees to 1.33 degrees. If the height of this crater shoulder is substantial, so sun will never set on the peaks of the crater shoulder. So this is the land of eternal lights. So this, you can just imagine the benefits of this. Suppose you go there and you just put a solar panel which rotates 28 once in 28 days. You have power to power throughout the day, all 365 days, 24 by 7. So that is a very interesting thing. And all the volatiles are available in the crater. So this is the place where you get plenty of power and you can use the power. And once the technology is feasible, you can somehow do some kind of experiment and dislodge the volatiles without disturbing and collect this material which is very useful. This is one of the important things of race towards the cold traps of the moon. Next. The helium-3. Helium-3 is the fissile material people are assuming which is available in plenty. So I may not give a very, very coherent, continuous thing, but idea is to explain you what we have done, something which we have done special. So, in 2008, what we have done. See, although we didn't explain everybody clearly, we lost both the star sensors in quick succession towards, say, I think 8th month or 9th month after launch. So it is almost like we had a blind satellite, and almost everybody was feeling that we will abandon the satellite. But we came up with a good idea, that is, we had a orientable antenna on the spacecraft. So with the orientable antenna, we knew if we orient the sun sensor one axis towards the earth or towards the sun, we know by geometry at that time of the day where is earth. That means we know the included angle between sun vector and earth vector. So this orientable antenna, we oriented such a way that it is along the expected included angle surface. So we know now if we keep this geometry and rotate with respect to the axis pointing towards sun, it will move on a cone described with the apex passing through the sun, and sometime during this revolution it is bound to find earth. So we switched on the transmitter and oriented the DGA, and we are looking for the signal, and we got the signal. And when the signal was maximum, we know that the antenna was pointing towards Earth station. So Earth station. So we had pre-computed this geometry, and we had transferred this so-called state to the onboard computer, and we have captured the all the three axes. See, one axis which was pointing towards sun, anyway it had captured two axes, and the third axis we captured with this knowledge. Once it is captured, all the three axes are known at that instant, and gyro was there to propagate the attitude. Although short-term stability of the gyro was quite good, and it was holding for some time, but this cannot go on forever because of the drift. So we had to correct now and then. This correction we could do very, very nicely during Ashtami, because sun vector and earth vector were perpendicular, and new moon day and full moon day, this geometry, the collinearity comes, and to resolve the earth direction was not easy. This was the limitation. Okay. And another interesting thing we have done is, in this condition, after losing both the star sensor, we had a wonderful opportunity there was a total solar eclipse which had occurred around this time. So we found out, you can see whatever is marked in red is the target we wanted to capture around this. This is the path of totality, whatever is written in red. So we had initialized the axis earth, whatever attitude, like I had explained earlier, with this attitude, without star sensors. So we know where is the earth. We started a slow rotation, and we switched on all our experiments. And about it captured some 7 rotations was there. By that time, our solid state recorder got full. So, and what we captured is this. Okay, now you may see recently, 1 year back, 2 year back, NASA, ESA, all the people are showing we have captured the total solar eclipse, all those things. But way back in way back in 2009, you can see 22nd July 2009, we have done this total solar eclipse capture. Can you see very clearly? There is okay. I don't have all the 7 slides with me. If you go to the net, there is a paper on this. You can see. Can you see a red circle, small circle, and a glint there, right side? That is the sun glint, and this is the moon's shadow, which is quite dark. Can you see here? Behave along the bright clouds. Can you see around shadow region? So this is what we captured during that. Next. So okay, when we set the motion running, the first picture came is this. So you can see the partial moon here and the sun here. In this, you can see very clearly the totality shadow. Okay, next. Okay, then we had so-called Abdul Kalam payload, which is a 40 kg moon impact probe, which was jettisoned right at the equator, and it went and impacted somewhere near the Malapart region, that is the southern, near the South Pole, 80 degrees and below, 80 degrees south latitude. That is named after Jawaharlal Nehru, and it is called Jawahar Sthal, because it was impacted on November 14, 2008. Next. Okay. Whatever I explained about the Lake Shackleton, so you can see whatever this ridge type of thing which is called Malapart, this is the place where this moon impact probe went and landed. MIP, you can see. And that is the end, you can see the Shackleton crater, which is having the lunar south pole. Next. Okay, with this, I have completed some of the interesting points, and I will be very glad to answer any question you have. Any question? Anything you can ask. So, Venkateshan, you can ask him.
Sir, Gurunath there. Why I did to...
Hello.
Yes, sir.
Yeah. Hello. Am I audible, sir?
Yes, you are audible.
Yeah, fine, sir. Yeah. So, about the students, sir. Yeah, students, we have the guests online, so we can ask questions. Introduce yourself.
Good afternoon, sir. I have a question. One is, how did really the orientable antenna help? I want some more insights about it. And I have one more question that I'll be asking.
Can you please repeat the question, please?
Yes, sir. I actually want to know how exactly orientable antenna helped in like when there was like.
Okay, to capture the attitude. Is it not? After we lose the star sensor, how did we initialize all the 3 axes? That is the question.
So the thing
With
is,
the orientable antenna.
yeah, like why couldn't we do it for long term? Why couldn't we do that for long term, sir?
Why couldn't we do?
Why couldn't we use orientable antenna to correct it in the long term?
Please repeat.
How, like, the orientable antenna was used to correct it in the short term? Why couldn't we use it in the long term, sir?
Okay. See, you know about gyros. See, these gyros, mechanical gyros, have excellent short-term stability, but on the long term they keep drifting. That's why you require a star sensor like inertial sensor to initialize the attitude. Once initialized, these gyros hold the attitude very well for a short term, but they cannot hold for days together. That is the problem.
So the sensor
Okay.
is doctor. So am I audible?
Yes.
The
You mean
sensor.
you mean the long term? Why we didn't progress using the same technique for a longer duration?
Yes, sir.
Because the AOCS failed.
Okay, we had
So the satellite became blind totally. We could not communicate with the satellite.
so we had more and more failures. Final failure, which was the last thing, was transmitter failure. So once the transmitter failed, we have no way of knowing what is happening.
So couldn't we use any other technology where we could solve the issue in long term so that it would run for few more months?
See, if the star sensor doesn't fail, we had fuel something at the time we abandoned the mission. That Chandrayaan had 130 kgs of fuel. That means fuel was not at all a limitation. Failures handicapped us. So you can see the similar hardware which was used in Mangalyaan, nothing happened. Years and years it went on. Hardware was the same.
But do we have any technology for it for preventing the drifting and making it for very, like, at least for few more months? Like, is there anything like that?
Okay, now technology wise, if you see, there are fiber optic gyros. We have which have extremely low drift. That way, if you initialize once, FOGs last for, I could say, some at least a fortnight without much appreciable drift.
Okay, couldn't we use that instead of orientable antenna?
Now, antenna was oriented just to get initialized like a snapshot. You capture the attitude and hold on to it. You hold on to it as long as gyros don't drift too much. Once the drift is too much, again it requires one more attitude capture.
Thank you, sir.
So we kept doing this. I think we would have done some at least 10 times.
Sir, I have one more question. What is the major difference between Chandrayaan-1 and Chandrayaan-2 and Chandrayaan-3?
Okay, Chandrayaan-1 was just a orbiter. This is the first stepping stone. Chandrayaan-2, we had a lander, orbiter plus lander, and a small rover.
There is a
And
probe.
it is okay. Now Chandrayaan-3 is much more.
Only rover.
Chandrayaan-3?
No orbit.
Okay. So these are the things. So mainly we had a reduced, very small rover and all. Okay. One interesting thing is when you land on the moon, you will have to land at the daybreak as seen in the moon. That means as sun just rises. So we have told you that 14 days of daytime and 14 days of night. So 14 days, that equivalent of morning. The morning is important because the sun elevation should just reach around 10 degrees so that the soil temperature will be at least some 10-20 degrees. once the soil temperature is 20 degree, the rover can get down. And before, okay, during the noon, sun is on the overhead if it is equator, but this landing site is mid latitude, let us say 70, 69 degrees thing. So maximum sun elevation will be only 21 degrees. So it is not as bad. So it is what we will say is it is a safe place to land, and they would have taken care of topological things. So main challenge in landing is the vertical descent. When you come down, after killing all the velocity, when you come down, the local gravity doesn't matter at all, but you will have to land perpendicular to the topology. So that means you will have to sense the topology so that you will not get toppled. The maximum descent at touchdown cannot be more than say 0.3 degrees, 0.3 meters per second. And all the three legs should be somewhat reasonably placed with respect to topology, not perpendicular. And there should not be any boulder so that there will be a toppling. Okay, next question.
Not audible.
You are muted.
Excuse me, sir. Am I audible now?
Yeah, no, yes.
Sir, if there is any like a launch in the future, Chandrayaan-4 like that, how will it be different from 3?
Not audible.
No, please
Can you
repeat
clear it?
Chandrayaan-4, what will be the Chandrayaan-4? It will look like the mission.
Chandrayaan-4.
Mission will be like, but we don't have any answer right now.
It depends
We
on
are thinking on Optimus.
Chandrayaan-3 outcome.
We don't know. Depends upon the next chairman and all. Or Rangarajan will be able to answer.
Yeah. So we have just Dr. S. Rangarajan on the online mode. So we all join to welcome Dr. S. Rangarajan. Please join your hands. Welcome. A big welcome to my campus, sir. Yeah, over to students again to the question and answer session. Rangarajan, sir, am I audible, sir? Yeah, okay.
He's muted.
Yes, I am muted. Please follow me. Yeah, yes, yeah. Go to the students once again. The questions.
Hello, sir. My name is Guru Dikshit. My first question is that the temperature in the moon, like the extreme conditions, are pretty extreme. So, what materials are we using to make the camera lenses?
See, okay, I will try to answer. The extreme temperatures are the environment, but we should manage within the system normal temperature quite close to the acceptance level limits and all. We cannot expect anything to function at the outside environment. But what normally people take care is they crimp the external cables, so the soldering and all they avoid so that there will be no disjoint, and all the lenses they will have adequately what standard glues and washers and all which will withstand all the temperature, and the extreme temperatures are not allowed to affect the electronics and hardware. See, Chandrayaan-2, in the beginning, we were supposed to go with the Soviets. Their plan was to have radioactive thermal generator. They had a plan to have 250-watt plutonium reactor, radioactive thermal generator. So that will do all the things. That is the type of approach normally people take when they go to the real poles. This is 69 degrees, which is not very really close to the pole. But when you go very, very close to the pole, you have to go with the radioactive thermal generator, or you should have an orbiting satellite which collects the solar energy, and through microwave beam it radiates to the lander or rover, as the case may be. Without these kind of technologies, it is impossible to go to 88 degrees and above.
And Mars also now, I am pretty sure that Perseverance uses a nuclear reactor.
Mars is not at all bad. Mars is a wonderful place. Temperature is not very bad, and 24 hours per day. Mars is a nice place.
No, NASA now uses a nuclear reactor in their current rover Perseverance to fuel the NASA. It uses a nuclear reactor behind the Perseverance rover to fuel it.
Okay. Just speak clearly. I am not able to get it.
NASA, the US space agency, it uses a nuclear reactor on its Mars Perseverance rover to fuel it now. So,
Okay.
why don't we calculate the idea of Chandrayaan?
See, on Mars, are you talking about Mars or Moon?
No, why don't we carry the idea of using a nuclear reactor in the back to fuel the rover?
Okay, radioactive nuclear
RTG,
reactor.
RTG, why not? We are using RTG, sir. On
RTG's problem is, by chance, if there is a launch accident, if you spill over the radioactive material, so nobody is going to excuse you. See, sometime back, long back, a Russian satellite which had a RTG spilled something on Canadian Eskimo land. They had to pay a lot of compensation. These are the risks, very big risks. You should be doubly and triply careful. And just before Chandrayaan-2 took off along with the Russians, there was an ambitious mission by Russia called Phobos Grunt. That had a propulsion problem, huge propulsion problem. And that time Russian economics also was not good. That's why our plan with the Chandrayaan-2 with Russia going to the real poles got cancelled.
And one last question. We know that the atmosphere of the moon is way thinner than what we have on Earth. So, do we use mechanical systems of braking, or do we just do it aerodynamically?
No atmosphere on the moon. No atmosphere.
How do we brake? Like slow, kill the velocity down?
It is through rockets.
Retrojets.
Rockets and all. Continuous mass expulsion.
So
Thrusters.
Okay.
So there is no atmosphere at all. Even 10 years atmosphere is also not there. Mars has got an atmosphere which is almost 1% of Earth, and it is mostly carbon dioxide. At large velocities, Mars can be having aerobraking. It can be used, and Mars can be used for parachutes. And you might have seen there was even a helicopter was used for Mars. All those things.
Yes, sir. Thank you.
Okay, one question, very nice question you should have asked. Why in moon landers and rovers are having problem? Why not in Mars? See, Mars, all the spirituality, this, that, they lived for 3 years, 4 years, 5 years. Why is that? Whereas on moon, you cannot even think of more than 1 month. Why? See, because on Mars, solar power is there and 24 hours day, and happily night is very small, and temperature is just negative, slightly negative topology, and it is like Earth. Mars is a weathered planet. Okay, then the rovers which work on Mars are like white collar workers. They get up at 10 o'clock in the morning, 4 o'clock they go to sleep. So this way they can go on. There is no life limiting factor on the Mars. That's why the rovers on the Mars, properly designed, lasted for months and months and years. That is the reason.
Yes, sir. Sir, I have a next question.
Yeah.
Sir, myself Hashir. And regarding the next question, sir, we were the first to reach the south pole of the moon.
This, if you call as the South Pole, yes, we are the first. I would not say it is a pole.
Yes, sir.
It is a 69 degree. 69 degree is not at all a pole, considering the moon's geometry. 88 degree and above.
Yes, sir. But the question is, why did we choose to go to the south pole?
Why do you?
Why did we choose to go to the south pole, sir? Like our rover will be there.
Okay. I just told sometime earlier, the best resources are available in the poles, mostly the South Pole, because South Pole has got more craters than North Pole. These are called as cold traps. The cold traps are supposed to contain volatiles like helium-3 and all, which are used for fission, easily used for fusion. Because of that, these volatiles, there is a demand to go to the cold traps of the moon.
Yes, sir. And many scientists are guessing that there might be millions of tons of water hiding behind this craters. Is it true, sir?
Millions?
Tons of water hiding below the.
Okay. Volatiles means water also included. See,
Yes.
these are all the small molecule, first few molecules like helium, helium-2, deuterium, then even water, all these things. Low atomic volatiles.
Yes, sir. Yeah, thank you, sir. So we also have one more guest, Jayakumar Venkateswaran. Sir, may I request you to enlighten our students?
Thank you very much, sir.
Thank you.
We will continue, sir. We want you on the online.
Okay. Thank you. I mean, like all our blessings of our seniors of ISRO and all, and our mentors. I would like to start project. I was a part of the co-founding member of Google Lunar Express mission. As you know, like as team members is one of the person. They are there, but I was the chief for the U.S. mission, America's dreams to go into the moon. So we got the finalist, but anyhow, but we could not able to reach the moon. But I could able to explain you something like the journey to the moon. So the thing is here you can able to see right now currently what I'm doing in now on moon exploration. I'm sending my DNA to the moon. This is the Lungri mission that is going to be happen by end of this year with the NASA Artemis program as a part of. This is carrying the DNA samples to the moon and something to it's a small nano lander. This is and I want to say something like, especially I'm focusing on lunar exploration, and my activities are engaged in human spaceflight training. For example, like astronaut training in Russia. So we offer training simulator to Roscosmos that we, train the astronauts to fly themselves to the International Space Station, something like that. So we do the professional astronaut training in Russia. And so I'd like to show you mean like the glimpses like how our moon mission has been like worked out. Can you please tell me the audio you can able to get it or not? This was the mission that we worked on previously. Be able to listen, get the audio?
No, sir, it's not. No, sir, we are
No audio?
You're clear.
Sir, audio, sir, video audio.
Audio is clear. Audio is clear as well. Audio from the video?
Yes, sir.
No.
No, okay.
Your voice is clear, but the media voice is not clear. So, like we can't hear the media voice.
Okay. Now I think it. Now you can.
No, sir.
Okay. So this was the mission we've been like as a part of team members also as a part of the like one of the India team, but I am the heading the US and international team that we pledged to go to the moon, and this is the we are trying to navigate and land on the moon with the spacecraft controls. So this is how the navigation to the precision landing on the moon. You can see the terrain. And finding the predetermined landing site on the moon. And Chandrayaan, it's like the last time it was in a crash landed, something like this. And this is the status we know. And once it's crash landed, I mean the connection has been normal. It will be the signal will be lost, and we'll search for the signal, and then we'll obtain and wait for the signal. So this was the previous status, but we can aim for our Chandrayaan-3 may get signal, we hope. And once we receive the signal, and we are down safe on the moon. And you can see the lander once after the landing. You can see the visibly the Earth, and trying to establish the communication with the Earth. And now we can see the ice through the rover, and you can see the controls of the rover, like the terrain, and also we can trying to predict. So this is how the rover will be released from a lander. And now we are never, I mean, like we're trying to see the lunar mobility, and controlling the rovers and trying to reach. This is the competition guidelines they set out. You have to reach, navigate, and you can move mobility access to on the moon surface by 500 meters. So then we get some money of something like nearly some $30 million. So unfortunately, we got and failed, but still we are working on the moon mission. And there may be a future spaceport on the moon. So this is what we are back to the moon, something like for good. That's what we are thinking on to do something. Hope you can see the video here. And I was in a part of the like witnessing the world's first living tissue has been like printed on the International Space Station. You can see this is the which I'm holding. This is the 3D bioprinter. We have tried to experiment with the like living tissue has been printed in a space station. So that was the world's first organ development experiment that we concluded. And now I wanted to do in the world's first bioprinting experiment on the moon that want to demonstrate it. And currently I have some working on the lunar regolith. We can able to make the 3D printing materials using the additive manufacturing technology. We can produce a number of materials that we can do. And I have something here to show. For example, I have some lunar samples that in regolith. I have some samples right now. I can show you here. You can see this. This is the samples that we have using the additive manufacturing technologies produced some of the components. For example, one second, I need to. Okay, no effect. Now you can see here. Now we made small wheels and some of the ceramic components. This and all, like I was in Russia 2 weeks back, so I brought it some samples that currently we are working on lunar regolith studies, like production activities, something like that. So what we can produce from the lunar soil, something like that. and the next will be the lunar factory, something that we could establish something on moon. And this is Team Indus side of it. Like I was in with the delegates from Vietnam, Prime Minister of Deputy Prime Minister of Vietnam, and a member of parliaments. They paid a visit to establish some cooperations. So now currently I am working on like my DNA I'm sending to the moon. They're using the NASA's one of the Artemis program, like Lingri mission to the moon. So this is, I can show you the spacecraft that what's going on. And currently, we are in the plan with the Synergy Moon, and we are developing on Lunar Cube, CS Lunar CubeSat, that was a part of Artemis program, and the negotiations are going on. And strategically, I'm planning on 24 in the between any launch window we can able to get to the moon. So I want to test the 3D bioprinting experiment that I want to do on the moon. That lunar Ligroth experiment that I am showing to the something like a lunar soil. Something we can try to fabricate using that materials. We can make some useful on-site production on moon institute production on the moon surface. So that we can do. This is what we are working on. And on the other hand, I'm working on cosmonautic training for V supply. We are assisting them. Like we developed the simulators for them to train the real astronauts, and we are working with them in Roscosmos for a long time. And now with Gaganyaan, we are also in the negotiation. Things are going on, and I want to establish some small center here. And something I think, I guess we are going to get some launch. I think, right? So we are, I think, getting limited. You wanted to see the live telecast. How is your plan?
Yes. Yeah.
Because can I make a pause? At least we can watch some liftoff, because we wanted to see and everyone want to see.
Yes, sir. Yes, that's what. Yes,
मिशन
sir.
की घटनाक्रम को पहले ही बताया जा चुका है। सर्वप्रथम दोनों S200 स्ट्रप-ऑन बूस्टर प्रज्वलित किए जाएंगे T0 पर। S200 के प्रज्वलन के 108 सेकंड के पश्चात L110, जो कि तरल-नोदक पर आधारित चरण है, इसका प्रज्वलन शुरू कर दिया जाएगा। S200 के प्रज्वलन के 108 सेकंड के पश्चात L110, जो कि L110 के प्रज्वलन के पश्चात तरल-नोदक पर आधारित चरण है, इसका प्रज्वलन शुरू कर दिया जाएगा। बूस्टर्स को यान से पृथक कर दिया जाएगा। L110 के प्रज्वलन के पश्चात करीब 137 सेकंड पर S200 बूस्टर्स को यान से पृथक कर दिया जाएगा।
Close to 1.5 minutes from the scheduled launch time. We are close to 1.5 minutes from the scheduled launch time.
मिशन होने वाला है। पूरे भारतवर्ष की आंखें इसमें हैं। सभी दर्शकों को ज्ञात है यह एक ऐतिहासिक मिशन होने वाला है। पूरे भारतवर्ष की आंखें इसमें हैं। इस यादगार पल के लिए यहाँ सब उपस्थित। अब हम उड़ान से 1 मिनट की दूरी पर अब हम उड़ान से 1 मिनट की दूरी पर
All sequences sound. Stage ready. -45 seconds. -40 seconds. L110 VHPP open. -30 seconds. -30 seconds.
Real-time programs activated.
-25 seconds. L110 VHPP open. -20 seconds. -15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Plus 5 seconds.
Liftoff normal. Here we have a majestic liftoff of LVM-3 M4 rocket carrying India's prestigious Chandrayaan-3 spacecraft.
P2 tracking.
प्रज्वलन और सफलतापूर्ण उत्थापन LVM-3 M4 रॉकेट का यह भीम का रॉकेट आसमान को चीरते हुए अपनी भयानक दहाड़ से चारों ओर कंपन उत्पन्न कर रहा है। इसे हम यहाँ महसूस कर सकते हैं और यही दहाड़ है जो वैज्ञानिकों को रोमांचित करती है। LVM-3 के उत्थापन के साथ ही हमारे अंतरिक्षयान चंद्रयान-3 की चंद्रमा की यात्रा प्रारंभ हो चुकी है।
As the rocket is soaring through the clear skies, every second moving closer to the accomplishment of the most important milestone in its mission to moon. Every Indian witnessing the launch live is content with the feeling of watching history in the making.
चंद्रमा की सतह पर अपना छाप छोड़ने के लिए चंद्रयान-3 अपने मिशन को पूरा करने निकल चुका है। वर्तमान में दोनों S-200 स्टेप ऑन बूस्टर सामान निष्पादन करते हुए अपनी निर्दिष्ट कक्षा की ओर बढ़ रहे हैं।
S-200 motors thrusting simultaneously, generating a peak thrust of close to 6,000 kilonewtons in vacuum. They are made of HTPB-based solid propellant, 204.5 tons in each strap-on. Close to 2 tons of propellant being burnt each second.
S-200 स्टेप ऑन बूस्टर्स का कुल प्रज्वलन काल 126 सेकंड का है और अभी घोषणा की गई L110 स्टेज का भी प्रज्वलन शुरू हो चुका है।
Apart from the strap-ons, the core stage has also commenced its operation. This stage, based on combination
stages are separated
of hypergolic earth storable liquid propellants UH-25 and N2O4. Now the S-200s have been separated.
घटनाक्रम के अनुसार इस यान से S-200 स्टेप ऑन बूस्टर्स को सफलतापूर्वक पृथक कर दिया गया है। यह काम सेपरेशन मोटर्स की मदद से किया जाता है। इसके बाद L110 तरल नोदक पर आधारित और विकास इंजन के साथ यह चरण सामान्य निष्पादन करता हुआ अपनी उद्दिष्ट कक्षा की ओर बढ़ रहा है। अभियान क्लोज लूप गाइडेंस के अंतर्गत है।
L110 stage performance normal.
The trajectory of launch vehicle is closely following the prediction.
Payload fairing separated.
जी हाँ, पेलोड फेयरिंग को पृथक कर दिया गया है यान से, क्योंकि यान अब 114.8 किलोमीटर की ऊंचाई प्राप्त कर चुका है। इस चरण का कुल प्रज्वलन काल 200 सेकेंड होता है और इस दौरान यह करीब 1600 किलो न्यूटन का प्रणोद उत्पन्न करता है।
We are 220 seconds past the launch time. Current altitude is 135 kilometers. In the 200 seconds of its operation, the L110 stage carries the rocket up to 175.5 kilometers altitude and imparts a relative velocity of 4.18 kilometers per second. That is 250 kilometers every minute.
L110 stage performance normal.
LVM-3 M4 रॉकेट का द्वितीय चरण पूर्णतः सामान्य निष्पादन करते हुए इस चरण में कुल 113 टन के तरल नोदक भरे जाते हैं। N2O4 तथा UH-25 अर्थ स्टोरेबल प्रोपेलेंट को ईंधन के रूप में प्रयोग किया जाता है इस चरण में।
Stage ignition is authorized.
अगला चरण C-25 का प्रज्वलन भावी है।
Plus 5 minutes.
L110 stage thrust cut off and separated. C-25 ignition command. 25 ignition confirmed.
That's a piece of really good news that the third stage has started its operation. The C-25 stage has been ignited.
जी हाँ, एक बहुत ही जटिल प्रक्रिया होती है क्रायो इंजन का इग्निशन, और इसके प्रज्वलन के साथ ही तालियों की गड़गड़ाहट से गूंज उठा है मिशन नियंत्रण कक्ष। तृतीय चरण C-25 वर्तमान में प्रणोद उत्पन्न कर रहा है। पूर्णतः सामान्य, सभी तंत्र पूर्णतः सामान्य हैं।
118 kilonewtons thrust in vacuum is what the stage develops with its 28.6 tons propellant combination of liquid hydrogen and liquid oxygen. Present altitude
stage
is close.
performance normal.
तृतीय और यह अंतिम चरण है इस यान का C-25। यह क्रायो ईंधन पर आधारित चरण है जिसमें लिक्विड हाइड्रोजन, लिक्विड ऑक्सीजन का इस्तेमाल होता है। इसमें कुल 28 टन का क्रायो ईंधन पूरी सुरक्षा तथा सावधानी के साथ भरा जाता है। इस चरण में 186 किलोन्यूटन का प्रणोद उत्पन्न होता है और यह करीब 640 सेकंड तक प्रज्वलित रहेगा। इसमें दिशा नियंत्रण के लिए इंजन जिम्बल का इस्तेमाल किया जाता है। क्रायो ईंधन का विशिष्ट आवेग 446 सेकंड के करीब होता है।
Currently, the rocket is at an altitude of 210 kilometers.
Plus 7 minutes.
While there is no much variation in altitude, this stage will add to the relative velocity immensely.
Cryo stage
आइए
performance
अब आपको
normal.
पेलोड के बारे में जानकारी देते हैं। लैंडर मॉड्यूल्स पे कई वैज्ञानिक प्रयोगों के लिए पेलोड्स लगाए गए हैं।
India's prestigious lunar landing spacecraft Chandrayaan-3 moving closer to its intended injection spot in the orbit. The propulsion module provides propulsion for earthbound maneuvers, translunar injection, and moonbound orbits. It also has a payload to study the spectral and polarimetric measurements of Earth and lunar orbit. The abbreviated name of the payload is SHAPE. Among the payloads of the lander module, the following are included. A Langmuir probe called Rambha to measure the near-surface plasma density, that is the density of ions and electrons, and its changes with time. The second payload is Chandra's Surface Thermophysical Experiment, or CHASTE, to measure thermal properties of lunar surface near polar regions. To measure the seismicity around the landing site and delineating the structure of the lunar crust and mantle, payload ILSA is there. The rover, after its descent, will further the
Cryo
scientific
stage
study
performance
objectives
normal.
through its own payloads. For better understanding of chemical and mineralogical composition of lunar surface, LIBS, or laser-induced breakdown spectroscope, is included. Another payload is the alpha particle X-ray spectrometer.
जी हाँ, लैंडर मॉड्यूल में 3 पेलोड हैं, रोवर में 2 और प्रोपल्शन मॉड्यूल में 1 पेलोड भेजा गया है। चंद्रयान-3 के स्वदेशी लैंडर और रोवर में नितभारों का इस्तेमाल किया जा रहा है। यह अंतर्ग्रही मिशन के लिए भी आवश्यक तकनीकों का प्रदर्शन करेंगे। लैंडर के पास यह क्षमता है कि वह चंद्रमा की उबड़-खाबड़ सतह में भी बड़ी सावधानी से उतर सकेगा और रोवर को बाहर लाने के लिए और संचार सुविधाएं प्रदान करने के लिए सक्षम होगा। चंद्रयान-3 के लैंडर और रोवर में कुल 6 नितभार हैं। रेडियो एस्ट्रोनॉमी of moon-bound hypersensitive ionosphere and atmosphere, जिसे शॉर्ट में रंभा कहा जाता है। यह चंद्रमा की सतह के पास प्लाज्मा के घनत्व तथा समय के साथ बदलाव का मापन करेगा। इसके बाद चंद्र सरफेस थर्मोफिजिकल एक्सपेरिमेंट चंद्रमा के ध्रुवीय सतह के आसपास की थर्मल प्रॉपर्टीज का मापन करेगा। इंस्ट्रूमेंट फॉर ल्यूनर सिस्मिक एक्टिविटी लैंडिंग साइट के आसपास के क्षेत्र में भूकंप जैसी गतिविधियों का पता लगाएगा। रोवर में चंद्रमा की सतह के तत्वात्मक विश्लेषण के लिए लेजर इंड्यूस्ड ब्रेकडाउन स्पेक्ट्रोस्कोप और अल्फा पार्टिकल एक्सरे स्पेक्ट्रोस्कोप इसका इस्तेमाल किया जा रहा है। एक बहुत ही दिलचस्प वैज्ञानिक निर्धार है शेप स्पेक्ट्रोपोलैरिमेट्री ऑफ हैबिटेबल प्लैनेट अर्थ, जो कि चंद्रमा से पृथ्वी से परावर्तित नियर इंफ्रारेड किरणों का विश्लेषण दूसरे जीवन सहायक ग्रहों को खोजने में मदद करेगा। वर्तमान में C-25 इंजन कार्यरत है और पूर्णतः सामान्य प्रदर्शन कर रहा है। अब हम प्रमोशन से 700 सेकंड की दूरी पर आ चुके हैं। सापेक्ष गति 6.5 किलोमीटर प्रति सेकंड, ऊंचाई 191 किलोमीटर।
As we have told you about the Chandrayaan-3's upgrades in the aspects of enhanced robustness through extensive ground tests and simulation. During the last phase of landing, the module will have a vertical velocity of less than 1 meter per second and a horizontal velocity of less than 0.5 meters per second from a height of 3 meters. The lander legs are designed to be robust enough to thrive the impact. The cameras are tuned to take pictures ahead of the landing and enable intelligent decision-making for choice of best location to land, avoiding craters and boulders on lunar surface. The successive pictures will also enable the craft to determine its horizontal and vertical velocity in real time. Laser Doppler velocity sensor is an upgrade in Chandrayaan-3 over its predecessor. It helps to determine instantaneous velocity of craft. Insights into the behavior of Chandrayaan-2 in the last few minutes of its descent has revealed to the scientists the necessity for upgrading the guidance algorithm. Inputs from various sensors are used by the autonomous navigation guidance algorithm of Chandrayaan-3 to plan the flight path to the most suitable landing spot. The engines of Chandrayaan-3 are capable of more gradual throttling also.
वर्तमान में हम प्रमोशन से 817 सेकंड की दूरी पर आ चुके हैं। करीब 950 सेकंड पर तृतीय चरण क्रायोजेनिक इंजन को शट ऑफ कर दिया जाएगा। और उचित अभिवृद्धि प्राप्त कर चंद्रयान-3 को यान से पृथक कर दिया जाएगा। चंद्रयान-3 को LVM-3M4 द्वारा एलिप्टिकल पार्किंग ऑर्बिट में लॉन्च करने के पश्चात 170 किलोमीटर की पेरिजी पर क्रमशः 5 बार मैन्यूवरिंग कमांड दिया जाएगा। 5वीं बार में यह पृथ्वी से चंद्रमा की ओर प्रस्थान करेगा, जिसे हम ल्यूनर ट्रांसफर ऑर्बिट के नाम से जानते हैं। फिर 5 अगस्त 2023 को यह चंद्रमा की कक्षा में प्रवेश करेगा और फिर क्रमशः 5 मैन्यूवरिंग के पश्चात प्रोपल्शन मॉड्यूल चंद्रमा की 100 किलोमीटर की वृत्ताकार कक्षा में स्थापित हो जाएगा। यहाँ यह उचित समय और अभिवृद्धि में लैंडर मॉड्यूल को पृथक करेगा और 23 अक्टूबर 2023 को चंद्रमा की सतह पर लैंडिंग की प्रक्रिया शुरू की जाएगी।
Plus 15 minutes.
We have come close to 900 seconds after the launch. Currently, the C-25 stage is thrusting. Current relative velocity is 9.29 kilometers per second.
जी हाँ, कुछ ही क्षणों में हम देखेंगे तृतीय चरण LVM-3 M4 रॉकेट का चंद्रयान को उद्दिष्ट कक्षा की ओर ले जा रहा है और उद्दिष्ट कक्षा प्राप्त होते ही और उचित अभिवृद्धि प्राप्त होते ही चंद्रयान-3 को अंतक्षेपित कर दिया जाएगा।
Cryo stage thrust cutoff. Satellite injection condition is achieved.
अभी पुष्टि की गई चंद्रयान-3 को प्रमोचन की कक्षा प्राप्त कर ली गई है।
Chandrayaan-3 satellite separated.
चंद्रयान-3 को सफलतापूर्वक अंतक्षेपित कर दिया गया है एलिप्टिकल पार्किंग ऑर्बिट पर।
Chandrayaan-3 has attained a major milestone successfully.
Chandrayaan-3 mission accomplished. Handing over to mission director.
This is mission director. The LVM-3 M4 Chandrayaan mission accomplished its precise satellite injection conditions. LVM-3 M4 mission is successful.
The launch has also added a feather in the cap of LVM-3 rocket. You can watch the jubilant congratulatory gestures of ISRO scientists in the Mission Control Center.
जी हाँ, चंद्रयान को सफलतापूर्वक अंतक्षेपित कर दिया गया है, लेकिन चंद्रयान-3 की यात्रा अभी जारी है। अब इस मिशन के बारे में हम अध्यक्ष महोदय से सुनेंगे और हम आपसे आज्ञा लेते हैं।
We sign off. Up next is address by Secretary DOS, Chairman ISRO.
Congratulations, India. Chandrayaan-3 has started its journey towards moon. Our dear LVM-3 has already put Chandrayaan-3 craft into the precise orbit around Earth. 170 by 36,500 kilometers was its intended target orbit, and it is precisely there now. And let us wish all the best for the Chandrayaan-3 craft to make its further orbit racing maneuvers and travel towards moon in the coming days. So let me wish all the very best to Chandrayaan-3 for its further journey towards moon. Before that, let me introduce the team behind this mission, the mission director, Mr. Mohan Kumar, and also the project director of LVM-3. And we have also the mission director for the Chandrayaan-3 craft, the project director of Chandrayaan-3, Veera Muthuvel. So over to them, Mohan.
Thank you, sir. Honorable Minister of State for Science and Technology and Departments of Space and Atomic Energy, Dr. Jitendra Singh, respected Chairman ISRO and Secretary Department of Space, former secretaries of the department, invited dignitaries, respected dignitaries and invitees, I am very happy to report here that the LVM-3 M4 vehicle has injected the Chandrayaan-3 satellite to the precise orbit, and once again the vehicle is proved to be the most reliable heavy lift vehicle of Indian Space Research Organization. Congratulations to the teamwork of ISRO family. I would like to appraise three things here. The vehicle systems are in the continuous process of quality improvement, especially in the event of our human rating efforts towards making the systems reliable. Secondly, the payload also, capability of the payload also is improved by mission strategies as well as vehicle engineering approaches. We are in the process of increasing the launch frequency of this vehicle considering the national requirements as well as satellite demands. Here, so many improvements we have incorporated in this vehicle. For example, the S200 nozzle, they are processed exactly as per the human rating standards, enabling us to have 100% NDT, and the inherent pocket erosion characteristics are removed. The L100 stage Vikas engine, mostly it is 100% qualified. Good. So we will describe all those details later because of shortage of time. Yes, sir. I take this opportunity to thank all the mission executives because mission executives for all the supports all along the launch campaign process as well as the launch. Once the launch manifest is released and mission executives are identified, really this is a penance of so many across the ISRO centers, our launch vehicle centers, VSSC, LPSC, IPRC, IASU, SDSC, SHAR, URSC and SAC, along with all our industrial partners, major players to the small-scale industries who supply us with all the deliverables in time, quality products, the suppliers of chemicals, propellant ingredients, suppliers of avionics systems, and our own GOCO facility operators. Actually, the industrial manpower is really our ISRO's virtual manpower. Everybody's efforts went into this, and also the prayers and best wishes of all our seniors, retired executives, everyone's prayers and our own family members. I take this opportunity to pray God Almighty for all the blessings in the form of this success, which was the penance by the ISRO family for last 73 days. And my prayerful pranams for the successful continuous operations of the Chandrayaan spacecraft, for its safe and soft landing on lunar surface and further experiments. Thank you. Jai Hind.
I thank the organizers, Dr. S. Kulkarni, Professor Chandrayaan-3.
Respected Chairman ISRO.
Today morning only we have celebrated his belated birthday. So wish happy birthday to Professor Chandrayaan-3 and the student.
Orbital parameters. Congratulations
So
and
I
thanks
also
to
thank
LVM3
the Stellar student group, Team Stella JCE, Team Nanam, Team EC Ordinary Club, IEEE student branch. Thank you very much. So we request the promotion of many more members to join this club so that many more activities can be brought out in future. Thank you very much. Thank you for all the audience. I was really, it's an overwhelming response. Very nice to see. Very nice to see. Thank you. Thank you.
Thank you very much, sir. We thank all the guests who spared their valuable time to share with the students. So I thank Dr. Hegde and Dr. Jaikumar and Anand Krishna. And we hope to have a continuous interaction. And after a few months for the launch of our own Jnanam JSS Nano satellite, we will all again assemble here and celebrate. Okay, I hope. Thank you.
Before we break up, we have a small video show for the Stellar class, right?
Don't close the windows. Open it. PPT आप है.
उनको स्ट्रीम करना ना. उनको स्ट्रीम करना ना.
Guys, ಏನಾಯ್ತು ಕನೆಕ್ಷನ್
Good afternoon. It is a great pleasure that I stand before you all today to introduce a phenomenal addition to our college community, the newly formed Space and Astronomy Club, Stella JCE. In a world filled with boundless mysteries and cosmic wonders, Stella JCE aims to ignite the passion for space and astronomy among our students, fostering a deeper understanding and appreciation of the vastness of the universe. Whether you're an experienced stargazer or someone who has only recently gazed up at the heavens with wonder, Stella JCE welcomes everyone with open arms. To kickstart our journey, we have an exciting lineup of events planned for the upcoming year. Stella JCE is not just a club, it is a gateway to the cosmos, an invitation to unravel the mysteries of our universe. Thank you, and may the stars guide us in our pursuit of knowledge and wonder.
Yeah, we are not presenting to those from camera, right? Next slide.
If you are fascinated by the wonders of space, eager to explore the mysteries of the cosmos, and want to connect with like-minded individuals, we invite you to join Stella JCE. Whether you are a seasoned astronomer or just starting your cosmic journey, our club offers a supportive and inclusive environment that nurtures your passion for all things space-related. Embark on a captivating odyssey through the cosmos with Stella JCE. Together, let us venture into the unknown, unravel the secrets of the universe, and foster a deep appreciation for the vastness and beauty of space.
So guys, everyone, thank you. We thank the Lord for joining us today in this event. This was the first event. We were not expecting this audience, but we are glad to see this audience today. And I personally, from my team, from my sort of team, I thank each and everyone. And let's hope for Chandrayaan 2.0, sir. So when we start working on it, we need your encouragement. We need more volunteers to come and join the club. So let me tell you briefly about the club. The Stella JCE has 3 wings. First wing is satellite development wing, where HOPSO will work on Chandrayaan 2.0 satellite and we will be sending it to ISRO HOPSO. And the other wing is the rocketry wing. So on rocketry wing, even regarding rocketry wing, we are trying to participate in the student rocket program funded by ISRO. And the last wing is the astrophysics. So anyone who is really interested in the astrophysics and deep space topics, you guys can take part in this club. So I personally request you all to come have a look at have a glance at this club and know what's there in the club. And I'm expecting more volunteers to come and join this club. And regarding the recruitment drive to the core, we'll be soon starting the recruitment drive. We'll be expecting you all to actively take part in the recruitment drive and support this.
I have to share this.
Thank you.
I have 2 more little introduction about the hardware club, easy hardware club. So these 2 clubs have been conceived by the department, and we want to lecture our students to just join this club, and we want to bring things which is there at your mind, the creativity at your mind. So therefore, the department thought of remote and freeze. It is up to take this club to the next level. So a small introduction from the founder member.
Freeze ಆಗಿದೆ. It's freeze. Remote ಅಲ್ಲಿ ಇದೆ. It's freeze.
Check master. Please, thank
So today we will gathered here, all respected teachers, dignitaries, and officials. Myself, President C, third member of the Harvard Club. On this very pleasant day, let me take a few minutes to introduce the Harvard Club to you all. The Harvard Club is now under the guidance of our respected teachers, Professor Tyagaraja-Murthy and Dr. Sudarshan Patil Kulkarni. They have been guiding us since the starting of our club and have been giving a lots of motivation for all of us. This club was formed on the idea of providing hands-on experience to everyone and fostering innovation and creating a trust about the hardware and interfaces. There's a saying that knowing a thing practically once is better than just looking at it 100 times. At the Hardware Club, we believe that learning is not just about textbooks and lectures. That's why we offer our members a unique opportunity to gain practical experiences in designing, building, and testing hardware projects. Our club focuses on providing opportunities for members to develop skills and knowledge related to hardware and software to foster a sense of community and encourage network among members. We also plan to collaborate with other organizations and individuals to promote interest in upcoming engineering technology. In addition to technical skills, Hardware Club also offers opportunities for soft skill development. Students learn how to work in teams, communicate effectively, and manage projects. These skills are essential for success in any career, and Hardware Club provides a supportive environment for students to develop them. Hardware Club is excited to announce our upcoming hackathon, where students from all engineering branches can come together to create innovative hardware projects. This event will provide hands-on experience and an opportunity to develop valuable soft skills such as teamwork and problem solving. We are also planning a speaker series featuring industry professionals who will share their experiences and insights with our members. This is a great chance for students to network and learn from successful engineers already on the field. We are also collaborating with the club Stella, whose outcome and project details will be shared with you guys very soon. So that's all for. Thank you. Have a good day.
Before we break for the tea and end the program, I request the 4 members to have a snack with the department and the faculty. So, please.
One space